Hello, fellow pedestrians. Until now, we were bothering ourselves with singular points, with power series convergence, and all of this. But why was that so? Why are we really examining power series? Now, let us assume a power series has a solution to a differential equation. We're talking about linear differential equations of second order. Now, this is a quite logical, quite sensible assumption one can make. It's a really educated guess. Why? Because power series can be functions that are analytical, meaning that many analytical functions can be expressed this way as a convergent power series for a specific range. Now, what that does, it does capture quite a range of solutions, right? So, assuming that y is a solution, where y is a power series going from 0 to eternity, infinity, I should say, is quite sensible. Now, the thing is that functions are not always nice to where I quote nice, meaning that the assumption works like a charm for this function, but what if we speak more generally and functions are not well behaved everywhere? Having singularities, discontinuities, etc., then this is a problem. So what happens here? So here enters Frobenius. Frobenius made an excellent educated guess where he proposed a solution of B of the form the previous, let's write it like this, the previous assumed power series AL XL, but he added an extra term. What that did was take care and regulate all of these discontinuities and singularities that greater range of functions now lie under, right? So this is a very bigger range of functions when you compare it to this. So you can also R can be anything now and can be negative, can be fractional power, can be complex power, etc. So it does account for non-analytic behavior, let's say. Uh, so we do have a huge variety of functions now. So after all of this being said, let's check this beautiful solution that Frobenius proposed. Now, what we do is we go ahead and set, let's say, goes from 0 to infinity of a constant, so this is a power series, plus another number. So y prime is going to be sum from 0 to eternity, al k plus l, x k to the l, and y prime prime is the sum from 0 to eternity of al k plus l, k plus l minus 1, x to the k, sorry, this would be minus 1, we just took the derivative, so this is k plus l minus 2. So this is all the transformation one has to do, has to take this and plug this in the second order differential equation. But of course we are far from done. Now, let's take an example and work our way through it step by step. Let's imagine we have the second order differential equation of the classical oscillator, where this is just a constant and this is 0, right? We take this and we plug them in this equation. So what we have are from 0 to infinity, a of L, k plus L, k plus L minus 1, x to the k plus L minus 2, plus omega squared, sum from 0 to infinity of AL, x to the k plus L, and this is 0. Now, from uniqueness of power series, the coefficients of each power of x must vanish individually. So the lowest order, the lowest power of x appearing is for L is equal to 0. So once we get this done and we plugged our expressions for y prime and y prime prime, what we're going to do, and we do this every time, we go and set L is equal to 0, but only for the lowest term. So let me write that down. For the lowest term, let's write it, which is this, we set L is equal to 0. And what we get is A of 0, k times k minus 1 is equal to 0. Now, the strongest assumption of Frobenius that I forgot to write down is that after all of this, a naught is different than 0. So the first term of the series cannot be 0. All the other terms can be 0, but assuming that this is not true, then Frobenius cannot be applied in the first place. So you will see why, because you will get later on a recurrence relation where all the other terms are going to depend on this term. So if this is 0, all the terms are going to be 0, but what this leaves is that you only get the most trivial solution there is. So Frobenius cannot be applied if this is equal to 0. So we'll always get an equation like this, where this is not 0, like we said. So we are forced to have this as 0. This is called the indicial equation. And from here, we are going to find the case, the extra term here, which will regulate the series solution for the particular differential equation. So what we find is that k can be 0 or it can be 1, right? Now, and like we said again, that if a naught is 0, then Frobenius cannot be applied because you only get the most trivial solution. Now, before we go ahead, what we can do here is check what happens to the next lowest term. As a general rule of thumb, when you have two powers that their gap is 2 or greater, then you can go ahead and check what happens to the next lower term. So if we had something like that, there wasn't really any point to do that. But now, because why? Because you can see why. Because the second lowest term is going to again be from here. Now, so consider the next lowest term, which will be in front of x to the k plus L minus 1. This term is going to be for L is equal to 1. So what we get is x of k, right? Sorry, this cannot be true because we would also have to include this. So this is 2. So what we are going to have is for L is equal to 1, A of 1, and this is for this term, right? K plus 1 times K is again equal to 0. Like we said, from the uniqueness of power series, its term of specific power of x should be 0. Now, for k is equal to 0, as we found, a can be anything, so it's arbitrary. For k is equal to 1, a1 should be 0, because for k is equal to 1, this is 2, right? This is non-zero, so this has to be 0. So choosing a k will have an impact of the next terms of our series. Now, let us choose k equals 0. It will we will soon show that choosing the greatest, the bigger from the two roots of the indicial equation um, would have a greater impact, meaning that it's a better practice to always choose the bigger one. And we'll show why. But just for educational purposes, let us choose k is equal to 0. So, after we've done all this, okay, we plugged every term in our differential equation. Then we found which k's, so which extra constants, are going to set the indicial equation to 0. Indicial equation is the one that has terms with a of 0, none other. So this does not happen for every differential equation, but it helps us to see how other terms are going to behave. Now, after we do all this, we go ahead and choose 1k, it doesn't really matter. Let's choose k is equals 0. And this is the tricky part. We need to set the net coefficients of x to the k plus 1 to vanish. So since L is a dummy index, right? L is just a dummy index, we can set it to anything. And of course, also the summations are independent. So what we're going to do, we're going to check this term and set L to j plus 2. It's like we're equating all these terms. So to equate this and this is just k now, right? So for this to be k, starting from 0, we need to send L to j, right? Sorry, this is k plus j. So for this to be k plus j, we send L to j. And we have sort of equated all of the powers of x. And now, what we're left with is go ahead and take all the terms. So this is going to be a of j plus 2, sorry, a j plus 2. This is k plus l, k is 0, and l is j plus 2. And this is the same as this, but minus 1, so j plus 1. Plus this term here, so only take the constants of aj is equal to 0. And what we are left with is this, and this is called the recurrence relation. We're going to use this relation to find each one of the terms of the series, so to actually find the series solution. So, no, let's go ahead and write this in this way. This is omega squared, so j plus 2 and j plus 1. Now, this, like we said, the recurrence relation, and what we're going to do is go ahead and start with j is equal to 0. So a of 2 is going to be minus, what is this? This is 0. Minus a of 0, omega squared, over 2. Then for j is equal to 1, we get a of 3 is equal to minus a1 omega squared over 6. For j is equal to 2, a4 is going to be minus a2 omega squared over 12, which a2 is this guy, so a0 omega squared over 24. Let's do a couple more, and there is a point to this. So a5 is going to be minus a3 omega squared over 20, which a3 is this guy, so a1 to the fourth, 120, and one last for j is equal to 4, we get a6 is minus a4 omega squared over 30, which is equal to a0 720. Right, now these are quite enough. Why are we doing this? We need to find a pattern. So this is there is not standard practice finding patterns. It's usually through mathematical induction, and the more you practice, the easier it gets. So let's go ahead and find possible patterns. Now you can see really fast that all these terms are the half of these terms have a of 0 and all the other terms have a of 1. So they can be split to odd terms and even terms, right? Because the odd terms all have a of 0, they do depend on 0, and all the sorry, that was backwards. These are the even terms that depend on a0, and all the odd terms depend on a1, right? This is why we said earlier that this cannot be 0, because all the terms are going to depend on this eventually. So this happens to give, okay, we have even terms. It can be written as 2n, because they're even. You will see a minus sign flipping for its, so let's go ahead and encircle the even ones with red, a4 and a6, right? And the odd ones with green, right? So the even terms, no, that's wrong. The even terms are a to n. We have a minus sign changing, so minus 1 to the n, and omega. What is omega? So this is squared. It's the same as this. This is fourth. This is the same of this. This is 6. This is the same of this. So it has to be same like this. To n, and the denominator is going to be, this is the same of this, but this is the factorial of 4. This is the factorial of 6, and of course this is also the factorial of this. So 2n factorial. Now, exactly the same way, the odd terms are going to be rewritten as a to the 2n plus 1 is equal to minus 1 to the n omega to the 2n over 2n plus 1 factorial. Now finally, we're ready to write down our solution. What was our solution? AL x to the L plus k. But we chose k to be 0. So this is our solution. And now, if you go ahead and write this, you will get terms of a0, which is 1 minus x squared over 2 factorial x squared plus omega squared over 4 factorial. This is not squared, this is with fourth. X to the fourth, etc. Plus a1 x minus omega squared over 3 factorial x to the third plus omega to the fourth over 5 factorial x to the fifth, and so on. So this can also be written, finally, we can divide with omega here, but we can also do it later. This can also be written as a0 to infinity of minus 1. This is why it is so helpful to write this down beforehand. To the n, omega x to the 2n factorial, plus a1 minus 1 to the n omega x to the 2n over 2n plus 1 factorial. Now, we can add, sorry, this was wrong, because we have omega to the 2n and x to the 2n plus 1. So, if we divide with omega, we can get omega x to the 2n plus 1. And what are those? These are the power series for cosine and sine. This is cosine of omega of x, and this is sine of omega of x. Exactly like it's supposed to be. So if you go ahead, this is just a standard differential equation with the constant coefficients, right? This is one of the first things that we managed to solve. You go ahead and solve it, you will indeed get these solutions. And it gets really tedious to solve it using the Frobenius method. Why is this? Because it's not supposed to be used for this kind of equation. This is just a model equation to be able to show how Frobenius works as a first encounter. Now, generally, when an indicial equation gives you two solutions, each of them are supposed to give you a linearly independent solution, right? That's not really the case though. As we can see here, we did get two linearly independent solutions, but only using one. We only used k is equal to 0. So what would happen if we used k is equal to 1, where a1 should be 0? Nothing. We will just get linearly dependent solution to one of those. So I guess we get or cosine or sine of omega of x. So having two solutions, two roots from the indicial equation does not guarantee us for any reason that the Frobenius method will give us two linearly independent solutions. This was just the case, but even one of them was able to provide it, and this is really an exception. Now, let us check by using our knowledge from our previous video, what happens to the radius of convergence? Where does this function converge? Of course, we know that sine and cosine are analytical everywhere and they converge to all of R. So we do found what was expected to be true as solutions. However, their corresponding series just happen to be written as known functions, as we've seen. Now, let's make sure that this series do converge for every x as we know to be true. So, using um, written as a series, which is minus 1 to the n, omega x to the 2n over 2n factorial, right? Now, if we take the limit, so if we use our ratio test, and this goes to infinity, un plus 1 over un, this is the limit, and goes to infinity of omega x to the 2n plus 2 over omega x to the 2n and 2n factorial over 2n plus 2 factorial, right? And what is this? Is the limit where n goes to infinity for omega x squared over, this simplifies to 2n plus 1 times 2n plus 2. And of course, the most relevant term in the denominator is n squared from here and here, the most dominant one, meaning that this goes to 0. And like we said, when this limit, this ratio goes to 0, then the radius of convergence is infinite, meaning that it converges everywhere. Why is that? It is because it was expanded around ordinary point, and of course, for cosine and sine, every point is an ordinary point. We didn't have any singular points at all in this differential equation. So it could also be, so if this was the first way proving that, the second way would be to say it was expanded around x naught is equal to 0, which is an ordinary point, and from the theory from the previous lecture, we know that when this happens, and this is a solution to the differential equation from Frobenius, then the range of convergence is going to be written as x naught minus r, x naught plus r. And because r is infinite, this is nothing more than minus infinity plus infinity. Right? Right. Now, how we know that the radius of convergence is infinite, it is because this is nothing more than the distance from the closest singular point, and there is no singular point with this differential equation. Okay, this is a practice that we can do in any differential equation, especially this, the second way, mark it with red, the second way. So the range of convergence can be used immediately before solving the differential equation. This can be used at first sight. Of course, after you identify any possible singular points that may be present or not. Okay. This, however, needs is needed the knowledge of the solution to be used. So we are going to use this second way every time. So this is why we introduced this theory at the previous lecture, because we can immediately show and have a clue of what's going on, right? Now, let's talk some more. before going to any other examples. So let's say some words regarding the roots of the indicial equation. And this is again very helpful, and we will see why. Now, uh, what we've done was to use one root to extract two linearly independent solutions in our specific example, right? Generally, let's say that we have two solutions where k1 is the largest, and these are some very useful tips. So, if their difference is an integer different of 0, the Frobenius will provide at least, we have at least one solution. We may have two, like we did in our example, where this was 1. So it was an integer different than 0, and it provide with two linearly independent solutions. So at least one solution when the larger of the two is picked. So we'll get a solution, at least one, of this form, a of L, x minus x naught L plus k1, which k1 is the larger of the two. Now, if this is 0, so if k1 is equal to k2, so that means this is a double root, only one solution. Is obtained. You can't have a second solution. You have a double root. Where here, you get at least one solution. And in the case, the remaining one, so if k1 minus k2, not an integer, then the second linearly independent solution is in order of the form L x minus x naught to L plus k2. Now, if for some reason the second solution isn't obtained, because this is also possible, there is a way to find it using some knowledge that we'll talk about, using something called the Wronskian. Now, hence, Frobenius promises at least one proper series solution, and the second can be easily obtained to be linearly independent for the two of them. And what you get finally is a full set of solutions for a second order differential equation. And like we said, when we were talking about first order differential equations, no third linearly independent solution exists here, like it was the case for the first order differential equation, where you couldn't have a second linearly independent solution, right? Now, what can also be said about the roots is the behavior of the series solution near singular points. In the previous lecture, we said that when examining singular points and which will be the range of convergence for its case, we said that we need to examine every time what happens if you expand. Let's say this is a singular point and we expand around this, so we use this solution. It's not usually the case, but an exercise may as well ask you to expand around a singular point, a regular singular point. We only expand around regular singular points, never around singularities or irregular singular points. So, what happens if you expand around x naught? If you remember, we checked that the radius of convergence, in this case, near singularities, the intervals of convergence, let's write it down, intervals of convergence around singular points. Now, we've shown that the intervals is x0 minus r and not plus r, right? But what happens at x0, right? We can predict the behavior of the solution near x0 without the need to solve the ordinary differential equation, just by checking the roots, again, the roots of the indicial equation. So you can get so much information so much early on. Now, for very small x minus x naught, the sum will approximate to a naught. So let's see why. In general, we have the first solution, which is x minus x naught to the k, al, x minus x naught to the l. Of course, this is always different than 0. Now, for very small of this, the sum will approximate a of 0, the first term, because higher order terms become negligible. Thus, for x going to x naught, near this singular point, y1 of x is going to be x minus x naught to the k1 a 0. So, what we can immediately see is that if we take the limit when x goes to x naught of this guy here, what is this? This is the limit of this, right? So we can have three cases. It could be 0 if k1 positive. It could be a constant, a naught, if k1 is 0, and it could diverge for negative k1, right? Of course, for our example, if you remember, we used a k is equal to 1 to 0. Sorry, and what we got as a result was two functions that indeed around the expansion point, which was 0, are finite, right? They were both finite, both cosine and sine. So you can see this is very true. Now, this is the case, of course, if you have a second solution from Frobenius, then exactly the same will apply. Now, what if you have a second solution, but it doesn't come from Frobenius? So, it can be proven, let's say, let's write second solution, not obtained by Frobenius method. It can be proven that the second solution will have this form, y1 of ln of x minus x naught plus x minus x naught to k2 minus k1, and the sum of the series, let's see, say r, x minus naught to the r, that's it, for r going from 0 to infinity. Now, this is not very useful in general, as we do need to apply the general method to find y2. We'll see what this method is. Now, if you do some tedious calculations, which we are not going to use, we'll show that you take the limit of y2 when x goes to x naught, you'll get exactly the same as you had in this case. So you get 0 when k2 is positive, a constant where k2 is 0, and again infinite when k2 is negative. And for the case where you have a double root, so the second solution, there's no other way to obtain the second solution but by finding a solution outside of Frobenius. So what this gives you, the second solution is going to be this guy here, but this 0. So again, you will get a 0 x minus x naught to the k times ln x minus x naught, which will give you 0 for positive k and infinity for negative or 0, right? And we'll check examples of the aforementioned later on, since our current differential does not have any singularities to work on, right? Now, let us close this lecture by talking about something called linear dependence. And how to formally find what this means, right? We talked about linear dependence in the past, and we were keep saying that we will do it sometime. This is the time. Now, how to know if two functions are linearly independent? Now, if the Wronskian of these two is different than 0, then y1 and y2 are linearly independent one another. And we can use the Wronskian to find a second solution. Why? Why? Because it relies on linear independence. Now, let's say what the Wronskian is. It's y1, y2, y1 prime, y2 prime. So y1, y2 prime minus y1 prime, y2. If we differentiate with respect to x, w prime, sorry, is y1 prime, y2 prime plus y1, y2 prime prime minus y1 prime, y2 prime. So this goes away, minus y1 prime prime, y2. And if we use our most general second order differential, which is this, equal to 0, this can be rewritten as prime is equal to y1 times minus p y2 prime minus qy2 minus y2 minus p y prime minus q y1, and lastly minus p y1 y2 minus y2 y1 prime. And this is nothing more than w, the Wronskian again, so minus p w, and this is just a separable differential equation. It has an immediate solution of e to the minus, like we know, p dx, right? Now finally, we know that this is equal to this. So y1, y2 prime minus y2, y1 prime, right? But this can be rewritten as y1 prime square, y1 squared. This is just some manipulation of y2 over y1. So this is equal to this. Now, if you do the calculation, what you will find is that y2 of x is nothing more than y1 of x times the integral of e to the minus p dx over y1 squared dx. And this is how we find the second linearly independent solution when it is not provided by the Frobenius method. We can also try this at the previous example. Let's say we only got the one, right? We only got the sine of omega of x. So what is this? This can be written as sine of x, omega of x, integral of e to the minus p. If you remember, p was 0 because the differential equation was y prime prime plus omega squared y is equal to 0. There is no p here. So e to the 0, this is just 1, so dx over v squared. And this integral is nothing more than minus 1 over omega tan of omega x, which is nothing more than a constant, which we do not mind, of cos of x, omega of x. So one way or another, you're going to get the linearly independent solution. What we do need from Frobenius is to provide us with a solution, and it absolutely does every time, especially except some special cases where a or not is 0 and some other cases. But if we have the first solution, we can only get the second linearly independent solution, right? And one can show using the Wronskian that there is no third solution. So if we get this, for three solutions, the Wronskian is going to be 1 prime prime, y2 prime, y2 prime prime, y3 prime, y3 prime prime. Now, if we use our solutions, so this is sine, this is cos, and this is omega cos of, well, omega x, etc., you will end up with something like that, because all the other terms are going to drop. But if we assume that this is a solution to the differential equation, then this is the differential equation, and this is 0. And if the Wronskian is 0, meaning that these three are linearly dependent. And we know that this and this are linearly dependent, meaning that y3 has to be linearly dependent to one or both of them. So there cannot be a third solution. And we've solved this using our particular example. Now you can do all the calculation. It's not that difficult, but we don't really mind it right now. So we'll end this lecture with some cases that we are going to examine or on the videos to come. So cases to examine, we can have double roots, we can have singular roots, meaning that it's only one, not singular point, of integer difference. We can have singular again roots of non-integer difference. We can have expansions around ordinary and regular singular points, but never around irregular points. Frobenius does not work around regular points, irregular singular points, sorry. Cases where the series are truncated, to a polynomial. Series cases where if not zero, where Frobenius cannot be applied. Cases where expanding around a regular singularity, where you could have either that this is true or that the limit, the ratio, is going to go to infinity. So it diverges everywhere. We'll see all this and more on our next video or videos on many examples using Frobenius. And it only gets better from here on. So thank you all for watching, and I'll see you soon on the next video.